All right, hello everyone. My name is Jeff Smith. I'm here from Facebook AI Research. And I want to talk to you today about PyTorch 1.0. The focus of this talk is going to be on this unique journey between the mode of research and production. And so one really helpful thing for me in getting to know your needs as an audience would be to take a really short poll. And so the poll is pretty simple. So first, which of you would identify with the persona of someone who does research? You author machine learning models, you train things like that. Who here would say that it's sometimes like think in the mode of a researcher? Okay, great. And so then who here would say that they support production systems, live products with users that need to like not go down and be efficient? Okay. All right. So that seemed like we skewed a little bit more towards the production end of things, which was kind of my expectation for this conference. In terms of my personal background, I've spent most of my time a little bit more closely aligned with production systems, but often for about the past 10+ years working on this specific problem. How do we take research into production within AI technology? And so that's what we're going to talk about today. Here's the scope of some of that. As you can see, I want to get some context on what we do with AI in products at Facebook specifically, and then dive into PyTorch as a unique technology that sits underneath all of them, and talk about how it can be used within challenges you might have when building products. Here's an intro to some of the things we use AI for. There's a broad range of things you can use AI for at this point in time. So this is an example of social recommendations, understanding what it is you're looking for and asking your friends. Next, this is my personal favorite. This is the one I probably used at the highest frequency. I used to live in Hong Kong, and I have a good number of friends who post things in Chinese on my Facebook feed, and I need a machine to translate that for me because I can't read the Chinese. Similarly, you may not have seen this feature in action depending on your personal background, but accessibility is an incredible application of AI technology where you can render content which would have been inaccessible to people with different abilities, accessible using AI comprehension of the content on the page or the screen. Those are existing products being made better with AI. There's also all sorts of stuff that you can do that you never could have done before. So these are examples of things like bots and assistants here. So conversational intelligent agents that allow you to accomplish tasks. This is an example of generated thumbnails. So when users upload videos, what is the best frame that we want to show when someone is displaying a preview of this video, doing that automatically at scale. This is an example of something. This actually renders an AR map. So these are augmented reality is a very exciting area in which Facebook is doing a lot of research and interesting product stuff in. And you see that in places like the camera stack inside Instagram and Facebook. As well as we're investing in VR hardware. And so this is things like Oculus Rift. And so you need a lot of ability to reason about things like a camera model and a person's experience of space as they move through it in a virtual reality experience. That's not all. Some of the things that people don't always think of as being powered by AI that really, really matter are integrity concerns. And so these are things that make your experience as a user of the platform a lot better. And so this is detecting when people are doing bad behavior like share baiting to protect, and as well as other things like spam or inappropriate content. We need to be able to classify those things very rapidly before they show up in someone's newsfeed. And then here's a really powerful example of suicide prevention. And so this is, there are all sorts of unique problems that can come out when you are actually working on the challenge of what people are interacting with on a social level in their human relationships. And so having AI technology that can rapidly flag issues and then begin to get people into those situations can be really impactful. And then there's this picture of things. And so the way that some people think about how do you build a system that does this, right, is Facebook uses an ad-supported model. So in addition to all the posts that you put up, your friends put up, there's some amount of sponsored content in here. And so we as builders of AI products really need to think about how to use AI technologies like PyTorch to be able to make good decisions to say what is going to be the best value for you over the long term, not just what is the most efficient way to serve a bunch of ads to make money. And so we've been able to make substantial advances within our use of AI technology to give you a better experience over the long term and think about ways to model that in ways that are far more sophisticated than will you click on this ad. So the field of AI is advancing very quickly, and we've seen major advances in a couple of the verticals. The challenge, of course, with AI is it's a very big, broad mission. In its purest form, we get to things like Ben Goertzel's formulation of artificial general intelligence. Where we do see really powerful successes recently are in areas like reinforcement learning, which had historically been quite challenging, but is now starting to come online in real products and systems. And we have some interesting open source projects in that area. Similarly, computer vision is in several of those examples I showed you. We were able to actually understand what's in a picture and be able to take action on it, whether that's to protect for content violations or something like that, abuse of the platform, or also those accessibility sorts of concerns. Also, natural language processing. So this is everything from machine translation to also the examples like suicide detection. We have the ability to address so many individual utterances people are making to others within their social network that our ability to understand that and act upon it greatly in a sort of rapid and intelligent way is really powerful for us. So we're excited to see those sorts of advances come online. To do this at the scale of billions of people around the world, we need to have a very capable way of moving from research to production. As I mentioned at the beginning, I'm actually from Facebook's AI research group. And so we are a pure research organization, doing open research with open data sets, publishing papers, and using open code. And so we do this very exploratory fundamental research. But then Facebook, as a larger entity, also would like to find ways to take research and bring it into production. And so that's really the deep dive we're going to do here, is talk about how we can make that journey using specifically technology that has just been built for PyTorch. But I'm going to start at a conceptual level. For anyone in the room who's built systems in this area before, you probably have something like a mental model like this in your head. And you can see that you have to go through all of these steps when you're trying to model a problem that is based on data and figure out how to build and train your model and then transfer it into production. And that transfer into production thing is actually the challenge that I think is probably the hardest one for us to think about. How do we do this effectively and really design the whole system to minimize the impact of that? Because when something is successful, we want to go all the way out and deploy it and scale it to billions of people. So that's what we're focused on, specifically within the PyTorch project, is to be able to minimize our total time here by really doing a very different sort of design to your whole AI platform to allow you to be able to get to deploy and scale so much faster in a way that there's just that a much smaller translation step out into production mode. And I'm going to go into a fair bit of detail about how we do that. So here's a sort of recent picture of what it looks like to bring AI models online at Facebook. And so they have different histories and they have sort of different challenges. I will show them in a little bit more detail, but here's the rough path, is that we typically do research in PyTorch, export to a format called ONNX, and then we use ONNX to import into our Cafe2 framework. So if you're not familiar with those stacks, I'm going to explain them a little bit more. So PyTorch in its classic mode originated within FAIR as a tool for researchers who wanted a high degree of flexibility and an extraordinary ease of use, a very Pythonic, user-centric mode that feels just like writing imperative, eager Python, as people have been doing since the existence of Python. It's very popular, and its users love it, and it really opened up a lot of possibilities for us to do exciting new things. Fairly recently, we created this thing in collaboration with others in industry, people like Microsoft and Amazon. This is the Open Neural Network Exchange format. If you don't work a lot within deep learning, you may not have come across this. This is personally one of the most exciting innovations in our entire field, from my personal view. I wrote a book called Machine Learning Systems, and in it you can see a fair bit of discussion around the challenges of how is it that we serialize and import in models. How do we actually say, save our work and reuse it and do all the things that we want to do around that. This is probably the biggest step forward we have made in an industry in terms of actually coming up with any sort of reusable standard for machine learning models of any form. This is really powerful. I really love this, and I think this opens up a lot of possibilities for us, and I think it's super important that we're doing this in an open, standards-based way that anyone can participate in. And lastly, that last step I showed you in our little flow of how a model makes its way out to production within the Facebook world is a framework called Caffe 2. Caffe 2 was developed at Facebook for explicit targeting for an explicit intention to be used at the scale of billions of users. Specifically, it performs 300 trillion inference predictions per day. That's what we're doing with it already. And so this is something that is extremely battle-hardened across servers and mobile devices, and it gives us the ability to have a very strong story about what it means to be ready for production. All right, so this is a workflow that we have done historically. I'm now going to talk about really the latest and the greatest, which we like to call PyTorch 1.0. Because we've used these modes where we prototype, and then we perform this transfer step, and then we deploy it out. But there's all sorts of ways in which we want to make this a seamless, low-friction process. Because historically, while all of these technologies work and have great properties, the fact is that they take time, and that there are difficulties in getting things all the way from research out to production. The sort of concept of what a PyTorch classic model might be can be quite different than what a static graph-based framework like Caffe 2 thinks it might be. So what have we done about that? We focused on building a new platform, which we call PyTorch 1.0, that really is designed to make this a very smooth transition from prototyping out to production. So what is PyTorch 1.0? I'm going to give you kind of a broad view of a full feature set for folks who are unfamiliar with the platform. And then I'm going to dive a little bit deeper into some of the specific stuff that you might want to take advantage of in taking a model from research to production in that full path. At its highest level, this is meant to be a seamless path to production for AI. It's an open and accessible platform that is usable by everyone around the world. And obviously, we've thought a lot about how you want to have a tool that makes this transition. Some of the things we talk about are that it should be fully loaded, that everything should be available in there for you, but that every little feature should be very opt-in. So this is not monolithic. This is meant to adapt to the problems that you have, and so to allow you to use the components that are most suited to the challenges you're facing. All right. So what are some of the things you want out of an AI platform? What are you actually looking for when you're searching around for something to solve for this for you? One of them is hardware efficiency. And so in a lot of production AI use cases, we have really tight latency constraints. We need to turn around responses within milliseconds. This also gets into the issue of whether or not we can afford to run these things at a sufficient scale. And so hardware efficiency is a major need, and often I think it sits better within a framework's concern rather than within an application level concern. That gets into scalability. And so depending on what you're doing, there can be some really hard challenges for folks who have been working on machine learning for 5 years, 10 years more. You remember how hard it used to be to do things like distributed training, and for that matter, multi-threaded model serving. There's a lot of difficult engineering work in there, and it's great to have it out of the box and work sort of uniformly. The last is it needs to be cross-platform. We build applications that run on servers and on mobile devices, and the world of hardware heterogeneity, as we could move into a world of things like AR and VR platforms, we only need yet more capabilities to have the same functionality work across a broad range of platforms. And that gets into things like we might need to remove Python from our stack in places. So when we built this platform, we had the advantage that we're not starting from scratch. We had these two very successful tool chains already in use with our system. And so what we simply did was we merged them. And we're calling that PyTorch 1.0. So let's talk about some of those things in there. So some of the things that are really exciting about PyTorch 1.0 is that it's extraordinarily fast in comparison to sort of PyTorch classic mode. And so we get to take advantage of some of the best-in-class libraries from people like Intel and NVIDIA. So those are things like cuDNN and MKLDNN. And we're continuing to improve this by adding yet more high-performance operators. And so these are the fundamental building blocks of what allow us to be fast in a production scale. Next is ONNX is a first-class citizen within PyTorch 1.0. And why that matters to you is that ONNX is a rallying point for a lot of development across the ecosystem. So this is both at the software level and at the hardware level, allowing you to do a lot of different things with an ONNX model. It becomes very portable across different tool chains and different technologies you might want to take advantage of. All right. As I mentioned before, distributed training, really hard. So real-world deep learning applications today, we're talking about clusters of GPU-enabled servers. This code is non-trivial. Getting really good performance out of very expensive hardware is a moving target, and it's a significant challenge. And so we've invested a lot here, and we still maintain a high degree of flexibility. And so we have our new C10D distributed training library. It itself gives you the option of 3 pluggable backends, which is really designed to adapt to the specific needs of the architectures of the models that you're trying to serve. I mentioned this before. This might sound strange from someone telling you that you should really use a thing called PyTorch. One of the key features of PyTorch is being able to get away from Python. And so I'm going to show this in a fair bit of detail. But the short version of what we're talking about here is for all sorts of deployment environments, you may not have the option of using Python. This is things like mobile devices. As you look into the future, this could also probably mean things like robotics. What we want to be able to do is be able to give you a highly efficient executable runtime for production that is as efficient as we can produce it. And so we've produced technology that allows you to do that. And I'll show you that as we get into our compilation strategies. This one is a slide I had to update just yesterday because in the original version of this slide, I said, oh, this is coming in the future. It was just released yesterday. So there's a couple of technologies we've released out here, FBGEM and QNMPAC. They serve the same sort of purpose. One is focused on mobile, one is focused on server-side inference. And this is an important but subtle detail. We use the technique of quantization to get extraordinary performance gains in using deep learning models. And so this is using the right level of precision for your application, both for runtime and performance, but also for impact on energy usage, which can be really important for things like battery life on mobile or things like server spend if you're operating at large scale. And as I mentioned, mobile deployment's not easy. If you've ever had to work on it, there's this huge array of different chipsets and GPU accelerators. We still have different frameworks that we need to address at a lower level. These are things which often don't really interest a person building a new machine learning application, particularly if they want to deploy it to both Android and iOS. We deal with a lot of this inside the framework to allow you to be able to deal with the constraints and the heterogeneity of the current mobile landscape. And so what we can offer today is the sort of battle-tested approach of Cafe to Go. You also have the ability to use ONNX to export to different tools. So there's the ability to do things like convert ONNX into Core ML for use on iOS devices. And we're going to continue to improve this so that you get a yet more seamless export to mobile from PyTorch with the least amount of work on your behalf. I want to give you a quick picture of where we are in time. So at PyTorch DevCon, about a month ago, we sort of announced our 1.0 developer preview, and we're shooting to launch the final version of 1.0 by the NIPS conference approximately next month. And so you can see that we have a lot of these new features here that I showed. And then by future releases, we're focusing on some of those other improvements to particularly export, quantization, and the support for some of the stuff going on mobile. So I want to talk about this thing in some detail. And so this is a really exciting next step. And this is the Torch JIT, our just-in-time compiler. And this allows us to do some pretty powerful things with models that are expressed within Python, but then get compiled down into extremely efficient representations. And I'll walk you through that in some detail. We sometimes call this thing the hybrid front end, and that'll become a little bit clearer as we walk through what we mean by eager and static in graphs in deep learning models. We can see there a definition of a normal program called an eager program, right? So that we have we have control flow there. And so we need to be able to rewrite that at times into a static representation. And so this is a big difference in deep learning frameworks historically, PyTorch being a major leader within the mode of eager dynamic graphs. And so we can see that simple little rewrite here. I think this representation shows it in our C++ API. And so you can see very minor rewrites to things like if clause, allowing us to call down to control flow representations that we can compile down into a static form that allow us to do things like give you extremely optimized performance on hardware. So the way that we think about this, right, is that when you're in eager mode, which is still available to you within Python, within PyTorch, you may want to just be returning the result of your neural network at a given point in time. Or you may also want to be exporting the graph. What is the actual total data structure of your program? If we're trying to make that transition to a static mode, the program itself only produces the graph, and then the graph itself is the thing that produces the result. And so we have the ability to now pass between these, and I'm going to show you how that works. Briefly, why do you care about this, though? Is that it's great to have the flexibility of having arbitrary control flow and having this Pythonic user-centric mode of interaction. People like to do this. It's a great way to develop new technology. It's very hard to optimize, and thus it's very hard to deploy, particularly when you have real production constraints, whether they be on something like a mobile device or on a server. Static graphs have the advantage of allowing us to be able to understand all the work that's being done, and thus we can do a lot of things to optimize it, make it able to deploy. But historically, we've found that in the research mode, the static assumption really gets in the way of the flexibility of designing some new things. So we need to have ways to work in both. All right. So as I mentioned, people really love this way of interacting with PyTorch classic interaction in this eager imperative mode because PyTorch programs are just Python. They look like Python. All the API signatures look very similar to NumPy. This is a very natural way that reuses a lot of people's existing knowledge. Today, we now think of this as, again, our challenge here is that we actually have to use Python to run pure Python programs, and thus we pay that performance penalty. We now call this Python eager mode within PyTorch. That is to contrast with this, the PyTorch script mode. So script mode is a new way of thinking about taking your program and incrementally evolving it so that it becomes more static in the ways that you understand the state of what your program needs to be, and sort of making that very smooth and simple transition from research to production mode. And so I'm going to show what that looks like. The key advantage here is that when we finish this journey, we're production ready. So here's a picture of our two ways that we can take an eager mode PyTorch program and evolve it into a static representation. Those are scripting annotations and tracing. The point is, once we actually make the transition to the other side of our diagram, we're ready for production. We can take advantage of all those capabilities. I'm going to walk through a fairly step-by-step example of different ways that you can take advantage of the PyTorch JIT to be able to incrementally evolve your deep learning program. First one here is we're showing how you can make a call to simply trace this. When we say trace, what we're doing is we're doing a single execution of your program, recording out all the operations, and then creating a static representation of this. This is really useful if you have something like the absence of control flow or a nice linear computer vision model. This is appropriate for a lot of different classes of models. And the nice thing is it's almost no code. We just said trace it. With that traced model, we can now use it to perform an inference operation. We can also take this in a bit more of a step-by-step manner. This shows how to use the annotations. And so we're taking a module, and we're going to turn it into a script module. And the one little addition I have to do is that. That's it. And so by saying that we have a script method here, we say that this part can be turned into something static. And so we're going to then compile that down to a highly efficient, optimized representation. This is saving it out to a file. Pretty simple stuff. But now we have a representation that can be used across runtimes, whether we use the sort of annotation approach or the tracing approach. This has really nothing to do with PyTorch. Just here's a rough skeleton of what a minimal C++ application is. This is meant to stand in for your model server, your application. just to give you an idea of how you would plug in a little bit of PyTorch C++ code if your model server happened to be something like a multi-threaded C++ application. To be clear, you don't need to roll your own model server depending on your application. If you're looking for things like server-side inference, we have great support and relationships with Amazon, Microsoft, and Google, who have integrated first-class PyTorch support into all of their relevant products. And so this is ready to go today. You can just go click and use it, even in its 1.0 developer preview edition. This is ready to go, and so you can use their model serving functionality if that's appropriate for what you're doing. Quick FYI, there's a little bit more to build a C++ application. The code is in the docs. That's not as relevant here because we want to talk about once we are actually using our models within production. So here, this is just showing what it means to actually then call that serialized, optimized model from our C++ application. It produced, and so this is just a call out there to make an inference operation. We have to build it because it's a C++ app. And then when we call it on our serialized model file, we get that prediction there. You will notice that the results here are exactly identical to what we would get if we used a PyTorch eager mode with using pure Python. The difference here is, of course, that we're getting vastly superior performance depending on the underlying hardware that we're able to take advantage of when we compile for that representation. So that shows you a full path going from your PyTorch eager mode model and incrementally evolving it out to something that can be optimized and deployed across highly efficient server runtimes and on mobile. Okay, so here's a quick overview of what can we do today. This is very much a moving target. We're continuing to add out new functionality to the PyTorch JIT. This is a major area of investment for us. We really want to make sure that whatever your program wants to express, that there's a good way to take those steps to incrementally evolve it out to something which can be sufficiently optimized on things like GPUs and on mobile devices. So here's the snapshot as we see it right now, but we're continually releasing new features. And so the docs and the repo are obviously the best place to see the latest and greatest. But you can already do a lot of adaptation of very real-world deep learning workloads. We test this on both reference use cases, things like ResNet, but also on our own products. And so this is pretty powerful today to be able to get enormous performance gains in that transition from research to production, really at the cost of a simple annotation. And as I said before, you can grab this right now. The developer preview is available on pytorch.org. We already have tutorials and documentation that show you how to use all of the new features. And this is moving fast, and you will continue to see new updates from us in the future. And so with that, that is all I have to present. I want to thank you very much for your time, and I can take a couple questions. But I'm also going to do office hours after this as well.
So if you're developing models, do you recommend like starting off in that kind of, I forgot the eager mode first, like
sure.
Ironing out your issues and then going to the script mode? Is that the kind of the workflow as it was intended?
Yeah, absolutely. And there's a benefit there that I showed that is if you're doing every step in that transition. The nice part of that is when someone is doing pure research work, very often they're not the individual who would be responsible for thinking about those production concerns, but you have a great way of capturing their true intent in a way that you can manipulate once you start caring about those production concerns. And so someone else can also just jump in there and start to play around with that in a way that's very non-intrusive. Tracing adds absolutely nothing, and then in the case of using annotations, you're purely just adding an annotation. But then you start to be able to tease out, do we have what we need for a production use case? Yes. It's a microphone if you want to use it. Or I can repeat the question.
Hello. Good morning. So how does exactly the annotation that converts the eager function to the script work? Like, how does it infer that an if statement should be converted to a script if statement?
Right. So the short answer is it's complicated. And so, I mean, from the user perspective, there's absolutely nothing you need to care about there. But what we actually do is in each of those cases, we're finding a representation that allows us to push it down to lower level operators. Very frequently, what we're concerned with, is there a way that we can translate this to an operator which a GPU can understand? So if you're familiar with like CUDA operations or something like that.
Do you actually parse the AST of a function or the code to do that?
So I don't actually run our compiler team, and so to a certain extent, I'm probably not the best person to answer your question to give you a detailed walkthrough of how we perform that compilation. But yes, we create an internal representation of what is the program. It's called I think PyTorch IR is probably the most legitimate name for that. And so we're able to translate that representation into something that we can then compile down to efficient operations, which are themselves comparatively more static, avoiding the need to perform like arbitrary Python-based control flow.